what happened before that?
Well, we don't know. So this is where it gets into a lot of speculation. And
Let's go. I mean,
let's go there. Okay, sure. So,
nobody can prove
the
you wrong.
idea of what happened before t equals 0 and whether there are other universes out there, I like to say that these are sort of on the boundaries of science. They're not just ideas that we wake up at 3 a.m. to go to the bathroom and say, oh, well, let's think about what happened before the Big Bang, or let there be a multiplicity of universes. In other words, we have real testable physics that we can use to draw certain conclusions that are plausibility arguments based on what we know. Now, admittedly, there are not really direct tests of these hypotheses. That's why I call them hypotheses. They're not really elevated to a theory, because a theory in science is really something that has a lot of experimental or observational support behind it. So they're hypotheses, but they're not unreasonable hypotheses based on what we know about general relativity and quantum physics, okay? And they may have indirect tests in that if you adopt this hypothesis, then there might be a bunch of things you expect of the universe, and lo and behold, that's what we measure. But we're not actually measuring anything at t less than 0, or we're not actually measuring the presence of another universe in this multiverse. And yet there are these indirect ideas that stem forth. So it's hard to prove uniqueness, and it's hard to completely convince oneself that a certain hypothesis must be true. But, the more and more tests you have that it satisfies, let's say there are 50 predictions it makes, and 49 of them are things that you can measure. And then the 50th one is the one where you want to measure the actual existence of that other universe, or what happened before t equals 0. And you can't do that. But you've satisfied 49 of the other testable predictions. And so that's science, right? Now, a conventional condensed matter physicist, or someone who deals with real data in the laboratory, might say, oh, you cosmologists, that's not really science, because it's not directly testable. But I would say it's sort of testable. But it's not completely testable, and so it's at the boundary. But it's not like we're coming up with these crazy ideas, among them quantum fluctuations out of nothing, and then inflating into a universe with, you might say, well, you created a giant amount of energy, but in fact, this quantum fluctuation out of nothing, in a quantum way, violates the conservation of energy, but who cares? That was a classical law anyway. And then an inflating universe maintains whatever energy it had, be it 0 or some infinitesimal amount. In a sense, the stuff of the universe has a positive energy, but there's a negative gravitational energy associated with it. It's like I drop an apple. I got kinetic energy of motion out of that, but I did work on it to bring it to that height. So by going down and gaining energy of motion, positive 1, 2, 3, 4, 5 units of kinetic energy, it's also gaining or losing, depending on how you want to think of it, negative 1, 2, 3, 4, 5 units of potential energy. So the total energy remains the same. An inflating universe can do that. Or other physicists say that energy isn't conserved in general relativity. That's another way out of creating a universe out of nothing, But the point is that this is all based on reasonably well-tested physics. And although these extrapolations seem kind of outrageous at first, they're not completely outrageous. They're within the realm of what we call science already. And maybe some young whippersnapper will be able to figure out a way to directly test what happened before t equals 0, or to test for the presence of these other universes. But right now, we don't have a way of doing that.